All right, welcome back. We have made it to day 17 of Advent of Code 2022. Let's just dive right in. Boom. Day 17, Pyroclastic Flow. Your handheld device has located an alternative exit from the cave for you and the elephants. The ground is rumbling almost continuously now, but the strange valves bought you some time. It's definitely getting warmer in here, though. The tunnels eventually open into a very tall, narrow chamber. Large, oddly shaped rocks are falling into the chamber from above, presumably due to all the rumbling. If you can't work out where the rocks will fall next, you might be crushed. The five types of rocks have the following peculiar shapes, where pound is a rock and dot is empty space. Okay, so we have a line, a plus, an angle, vertical line, and 2 by 2. They fall in the order shown above. First, so this falls first, then this, then this, then this, then this. And then it repeats. The rocks don't spin, but they do get pushed around by jets of hot gas coming out of the walls themselves. A quick scan reveals the effect the jets of hot gas will have on the rocks as they fall. This is your puzzle input. For example, suppose this was a jet pattern in your cave. In jet patterns, less than means a push to the left, while greater than means a push to the right. The pattern above means that the jets will push a falling rock right, then right, then right, then left, then left, then right, then left, then right, then right. Yeah, you get it. When we get to the end of the list, we start over. The tall vertical chamber is exactly 7 units wide. Each rock appears so that its left edge is 2 units away from the left wall, and its bottom edge is 3 units above the highest rock in the room, or the floor, if there isn't one. After a rock appears, it alternates between being pushed by a jet of hot gas 1 unit, in the direction indicated by the next symbol in the jet pattern, and then falling down 1 unit. If any movement would cause any part of the rock to move into the walls, floor, or a stopped rock, the movement instead does not occur. If a downward movement would have caused a falling rock to move into the floor, or an already fallen rock, the falling rock stops where it is, having landed on something, and a new rock immediately begins falling. Drawing falling rocks with at signs and stopped rocks with pound signs, the jet pattern in the example above manifests as follows. And you can see that it's first, the horizontal line, then it's the plus, and then it's the angle. And it shows you can kind of follow the you can follow the pattern. You can see that it goes, okay, starts here, moves to the right, falls down, wants to move to the right but can't, falls down, etc., etc. And then it shows, when the next few rocks begin falling, this is what it would look like, which is super handy because then you can compare, whatever you have to this. I had to do that a number of times. Anyway, to prove to the elephants that your simulation is accurate, they want to know how tall the tower will be after 2022 rocks have stopped, but before the 2023 rock begins falling. In this example, the tower of rocks will be 3,068 units tall. How many units tall will the tower of rocks be after 2022 rocks have stopped falling? Alrighty. Yep. Let's take a look. So I start by defining the shapes. I sat and stared at this for a long time. I don't particularly like this, but it works. So this is what I went with. So basically, I have shapes is a list of lists, where each list inside shapes represents one of the shapes. So the lines that are involved in that shape. So here it's just the one line with the horizontal one. And here we have the plus and the whatever, and I formatted it so that we can. It's easy to see what's going on here. Then we set the silo width to 7. Do they call it a silo or tube? Doesn't matter. You know what I mean. Silo, and it's 7 wide. Then we have part A takes the file name and the number of total shapes and calls do the stuff. All right, so let's take a look at do the stuff. do the stuff is the one where obviously all the stuff happens. So we get all the lines, and you can see that the input is just one line. The same for the real input, way bigger, but still just all on one line. So moves is all of our moves, and if I take silo as an argument, so you can pass in like an existing one for some reason if you need to. If you don't, we just start with an empty silo. So the silo is another list where the first element is the bottom of the silo, and the second element is right above, and so on and so on. So it's going to be 0 indexed. The floor is at -1, and it goes up as the y coordinates increase. Right. We have some bookkeeping. I is for the shapes, and this is for the moves. This is stuff that's for part 2. So ignore that for now. Okay, so we iterate through this loop until we've put in all the shapes that we are asked to. So 2022. So we use the I modulo the length of shapes to index into shapes, and that this makes it so that I keeps increasing, but it just keeps looping through the shapes, starting over when it reaches the end. Again, this part is for part 2, so just ignore that for now. So once we're done here, we have this shape as in the shape variable. Cool. And per the instructions, each unit appears so that its left edge is 2 units away from the... I don't feel like I read that to you. Really? Did I? The rocks fall in the order shown above. The rocks don't spin. For example, jet patterns, 7 units wide. Yeah, the tall vertical chamber is exactly 7 units wide. I don't think I read this. Each rock appears so that its left edge is 2 units away from the left wall, and its bottom edge is 3 units above the highest rock in the room, or the floor if there isn't one. Maybe I did. Anyway, now I definitely read it to you, maybe twice. You're welcome. All right, so again, that's what it says right here. It appears left edge is 2 units away from the left, and its bottom edge is 3 units above the highest rock, or the floor. So we set x to 2 and y to, so the length of the silo plus the 3 spaces plus the length of the shape. Length of the shape is, the length of the list containing the lines of the shape. So this is the height of the shape. So the first one was just a horizontal line is just 1, and for the plus it's 3, and so on and so on. And then -1 because we are because it's 0 indexed, and that's just what we need to do. Okay. Then we have this loop where we implement the mechanics of the rocks, or the physics. They get pushed around and they fall down, and eventually they settle. So just like with the shapes, we have a variable that iterates through, or that just increases, and then we call, we get the remainder by division with length of moves, which again just means that we go through all the moves, and when we hit the end, we start over. And then we increment j. And then we see here if, if action is less than, then the new x is supposed to be one more to the left, unless we hit the left wall, in which case we just stay where we are. And same here, if action is greater than, then we set the new x to yeah, that's never gonna be true, is it? Oh, I guess it could. Yeah, anyway. We do bounce checking in here. So the next thing we do is, if the move wouldn't cause overlap, move the piece, otherwise do nothing. So let's look at would overlap. This was very fiddly for me. I looked at some of the other people who solved this, and some of the solutions I saw were really elegant. They were somewhat slower to run than what I came up with, but really elegant. But this is what I came up with. I might change it later because this could be done a lot better. Okay, so first thing we do is we check if we would stick out on the right side. Wedge is just as bad. I must have had another check here because this just as bad as what? What am I talking about? Okay, so if x plus the width of the widest line in a shape, I'm pretty sure I made sure that they are all the same width within each shape, but whatever. Yep, so if x plus the width is greater than the width of the silo, then we return true. We would overlap with something. So basically it's not a valid move. So failing that, we already checked, for going to the left if that would do anything, and then going to the right. So next up is go through each line of the shape. So yeah, I needed all these comments for myself. They're not just for you. This took this took me a long time. So we can't extend the silo until we finally add the shape to it. So if the line is above the highest known line, it's bound to be clear. Oh, we don't. Yeah. Okay, so at any given time, the silo is only defined up until the top bit of rock. We don't extend it until we know where it settles, and then we put it in. You'll see later. Okay, so if it is above what is defined in the silo, which is what we check here, then we know it's going to be clear, so we just continue. If instead we are beyond the bottom, that's also bad, so we return true as well. And finally, we grab that line that we are looking at. If these two checks pass, we grab the line, and then we go through each character of the shape and see if the pound signs in the shape, if where they would go is already taken. So I do that by calling enumerate on S. So S is the line of the shape that we are currently looking at. Okay, so let's say for this shape, this would be on the first go through, we would be looking at this line, then this line, and finally this line. But let's just say that we're looking at this line for right now, okay? So enumerate takes a list and returns, it says right there. So it gives us So tuples that have the index and the element. So the first element in the list is going to be returned along with 0, and the next one is going to be 1, and the second element 2, and the third element, etc., etc. So that's what we have here. So C is that character from the list, from the line, and J is the index of it. And then we check if it is not a blank line, in the plus, for instance, we have the corners are blank. And if they're blank, we don't care. They can overlap all day long, it doesn't matter. So if it's not a blank and it is also not blank in the line that we're looking at, that means that we are overlapping, and then we return true. And we go through this list or this loop for every line of the shape. If we don't find anything, then we're done and we return false. So there's no overlap. Boom. Yeah, a lot of work to get there. Not particularly elegant, but it works, and it's what we got. Yep. So if that would not overlap, the horizontal move, if that wouldn't overlap, we change X to what the new X would be, and we move on to the moving down part from the instruction. So we move down. If that wouldn't overlap, we subtract Y, and we drop to the end of the loop. We start over with the next move. If it does overlap, i.e. we can't move down, that means that we have found the final location of it, and then we add it to the silo and start over. So add shape to the silo. You input the silo and the shape and the coordinates of its top left corner. And what do we have it? Yep. So, yep, this is the first thing we do. We make sure that we have the space up top. Like I said before, one of the things we make sure that whenever we're going through this, we always know that there aren't going to be any blank lines at the top. We only add whatever we need, and that makes some of the actual thing we need to check for, which is the height, makes that a lot easier. Yep, so we go from the current height on to where it needs to be, and we append empty lines to the silo. Cool. And then we do pretty much the same thing as we did up here. We have two nested loops, one where we enumerate the shape. So this gets, I is 0, 1, 2, and S is, first line of the shape, second line of the shape, third line of the shape, like that. And then we enumerate the that line. So we go through each character in the line, and if the shape has a pound sign in it, then we set that corresponding spot in the silo to a pound sign. The reason for this check, man, this one cost me a lot of time, is that I forgot about that. So I would just place, when I wanted to place this shape at some given coordinates, I would cancel out, if these covered something, I would copy this empty space into the silo, and it would yep. And that was it, actually. Once you're done with that, you do the stuff returns to silo, and this possible period is for part B, so ignore that for now. So it returns all of this to part A, and part A just returns the length of the silo that it gets back, and that's our answer, and that's what we get here. Boom. Very quickly. Both for, this is the answer that we were looking for from the puzzle. Yep, 3068. And then mine was 3186. Yep. Cool. All right. Part 2. The elephants are not impressed by your simulation. Aww. They demand to know how tall the tower will be after... so what is that? That's 1,000, million, billion, trillion. 1 trillion rocks have stopped. Only then will they feel confident enough to proceed through the cave. In the example above, the tower would be, gosh, thousands? Yeah, thousands, millions, billions, 1.5 trillion-ish. So how tall will the tower be after, 1 trillion rocks have stopped? And obviously, it doesn't matter how how fast this is. This is going to take forever, right? We have to find a better way. And the thing to realize here is that everything goes in a loop, right? Everything's in a loop. The moves are in a loop. The shapes are in a loop. There's bound to be a pattern that emerges somewhere in the silo. So we just have to find that pattern, and that's what we're doing in part B. Because as soon as we have the pattern, then we don't need to actually compute what happens for each individual rock that falls down and generate the whole silo. We just know that, okay, if we are beyond a certain point, then for some number of rocks, we are going to see the same pattern going. And once we have that, we can calculate what it's going to look like if we were to add 1 trillion rocks to the silo, tube, whatever. Okay, so let's take a look again. So same thing. Let's see, part B. Okay, so again, we do the stuff, and just kind of randomly, I do 10,000 shapes. I did some experiments at some point that suggested that that's how many I need. That's actually interesting. So what is that possible period for the big one? Anyway, so possible period. And the way that I find that is... So, this is a bit of an optimization. Never mind that. If the length of the silo, so if we're already taller than 200, I added this check because there needs to be enough of the silo for the comparison to even start making any sense, because any one line is bound to repeat all the time. So we need to compare chunks of lines, and the more lines we add, the more confident we can be that actually is the same pattern, or like the exact same thing, that it's going to repeat itself again with that same period. And just each one line is going to repeat frequently, but not at a given period. So we say that we want 35 matching lines. I don't have a good reason for that number. I think I just pulled it out of my behind, and that's it's fine. And then I come up with a key. So in addition to matching the lines, I want to make sure that we're at the same point in our looping through the shapes, because if the lines match but we're at a different point in the shape loop, it's a fluke, right? It has to be a fluke. There's no way that what happens next is going to be the same if we're not dropping the same shape next. And the same with the moves. I want to make sure that we are at the same point in the in the moves, in the order of the moves. So yep, Mikey. So the point in the shapes, the point in the moves, and then finally the 35 topmost lines of the silo. I want those to be the same. So this is an integer, and a string. So they are perfectly hashable, and that means we can use them as a key in a dictionary. So that's what we do. We have we create this scene dictionary, and yeah, so we find the key. If we've already seen the key, then we assume that the period is so scene key tells us when did we see this the first time, or when did we see this the first time? And then we subtract our current position from it, and that tells us what the period is going to be. And sometimes it takes a while before you can establish the pattern, so you need to go a certain distance into it before you can assume that the period is going to work. And that is why this possible period, I call it is definitely the period. I didn't have the confidence in that on the first go through, so I called it the possible period. I had a lot of code later on to validate it. I would follow the period like 20 times in to make sure that it matched, because apparently I wasn't as good at. I think that was before I had picked a really good key for this, so it would find things that seemed like matches but weren't. But this is what it is if we've seen this pattern before. So if the top 35 lines of the silo, and if we've seen that before at a time where we were at the same position in shapes and moves, that's our period, and then we store that as possible period. Yep, and then we just keep going through the whole thing like before, and ultimately return the silo and the possible period. So we go through 10,000. Hopefully that's enough to find a period. In practice, and it turns out that it is. Maybe it wouldn't be always. Maybe there were different inputs where it wouldn't be, but this was sufficient for me. Yep. So we get the period and we get the base, and there was a lot of assertions here because, the number of assertions in my code is probably proportional to how fiddly something turned out to be, or how much help my brain needed to keep track of things. So this was my way of making sure that the result is actually correct. And to do that, I calculate what is it at the base. That is where the first time we saw a given pattern. Then we calculate what if we move forward one period, what if we move forward 2 periods, and then the difference between these two should be the same as the difference between these two. Otherwise, something has gone horribly wrong. Yep, and then we have this part A thing where we're cheating a little bit. And so we have the desired number of pieces, 1 trillion. This is a pretty nice thing in Python. You can You can add underscores anywhere you want in an integer to help you read it. And yeah, the anywhere thing is important. Actually, it's not just always 3 at a time. In India, for instance, they have lakhs, and which are 100,000s. They put the yeah, they're not 1,000 separators, but they put the separators in different places. So you can do that. You can put underscores in integers anywhere you want in Python, and it's just going to ignore them when it when it actually assigns the value. So this makes it a lot more readable. But we have our base and we have the period. And yep, so we take how many pieces we actually want, and how far is that from our base, and divide that by the period, integer division. And that gives us how many periods it is, and then we calculate the new base. So yeah, where do we need to calculate up to before we can start making assumptions and just move ahead these many periods? Yeah, again, yeah, this assertion is obviously always true, but I couldn't brain when I did this. So if that's good, then we set the base to this. We calculate what we would get at this base. Then we add the period, and then we know what the difference is going to be between. Yep, there's another assertion. Okay, so what if we take the result of the base case, and we see what does each period add, and then we multiply that by 10? What if we calculated that, brute force? Does that give us the same thing? Yeah, it does, because that's how this works. But I needed to make sure, because I was struggling a lot. And then finally we just return the answer, and yeah, you can see that it's not even a... Oh, what did I change? Because it's way slower now. Anyway, about a second, and that gave us the right answer. Yeah, this one wasn't. This one wasn't particularly interesting, I think. Maybe there were other solutions where you would find some interesting algorithms to help solve some of this. I don't know, but the way that I did it was just it was awkward. It took me a long time to get this done, but mostly because this fiddling around with the shapes and whatever, even seeing the elegant way that some of these other people who play the game have done it, I do like that better in some ways, but it was a lot slower for various reasons. So I didn't entirely like that either. I don't know. Maybe I'll have an epiphany at some point, and then I'll come back and change this. But for now, this apps, I'm looking at the code without showing you again. Got to get used to this. Sorry. Yeah, this is what I came up with. I think we can do a better job with it. I think it can be cleaner. Probably not much faster, I think, but this is fine. Took a long time, wasn't particularly hard, just awkward. But yep, I hope this was helpful. And if you have any questions or comments, leave them below. And otherwise, like and subscribe, and I will see you next time.